As we conclude our presentation session, join us for a glimpse into the future of motorcycle simulation with Diego Minen, Chief Technology Officer at VI-Grade. In this final presentation, he'll unveil VI-Grade's vision and plans for a revolutionary motorcycle riding simulator. Stay tuned as we explore the development and validation process, promising to reshape how we understand and experience motorcycle dynamics.
Yeah, thanks a lot. It has been a few years that I've been working on this motorcycle simulator concept, let's say. As you all know, we use intensively simulation for simulators. Seems to be obvious, but not always. And we received a patent also, by the way, covering all the principles of innovation and originality and so on for this simulator. And I tried to give you in this presentation some of the ideas that are behind, also completing basically what Enrico told you with the interesting work they did on the virtual rider for several years. Basically, there are a few motivations for us coming up to the development of a concept. By the way, it could have been more a physical realization of the concept. A couple of years ago, I was that close to start the development of this, but for several reasons, including COVID and others, it was not possible. But let's say we are more ready to start. So, being a motorcycle rider myself for a few years, it is very difficult to think that you can control in open loop a motorcycle like you do for a car. Then, as Enrico has told, accurate modeling of human-like rider is not always possible with algorithm. There is an increased complexity of physical model performance, which justify clearly the usage of those for feeding simulator. Increased quality of road and tire modeling, as Flavio has presented before. And also, among several other things, there is an increased usage of any type of control system in the motorcycle, like is happening with the cars. And of course, the level of risk that you have testing all this together with a human rider on the motorcycle is very high. So we have identified some of the characteristics of a possible motion platform that could do the job for moving, let's say, at least as a rigid body, the entire bike. But we also consider that we want to put a rider on it, and not a rider like a bag, a passive bag, but let's say a living rider, alive and kicking rider. And sometimes it's very important to kick the bike or not to kick the bike. And for this reason, we had listed here several different aspects. If we are more focusing on ride and handling, or handling and ride, or steady handling. As you know, steady maneuver are the most difficult to obtain on any type of simulator, because a simulator for terrestrial vehicle at least, should have a certain workspace and should always go back in its position. And this is not ideal for developing stationary acceleration. You would like your simulator to continuously move somewhere for you to continue to, let's say, experience acceleration. That's not possible, and so what can we do? First of all, showing this new concept platform that we call Hexarot. The Hexarot is a new type of, also this has been patented independently for the motorcycle simulator, is a new mechanism that is a 6 degree of freedom mechanism which has certain characteristics that are quite interesting from many aspects. We have basically the aim. We have the concept of trying to maximize the simultaneous motion of the platform, not one single degree of freedom, but more contemporary, and that's very important for motorcycle dynamic, with minimal latency, with minimal noise, with maximum possible frequency response, with also easy, from the point of view of mechanical parameterization, easy parameterization. So the concept I think, is quite simple. There are 6 crankshaft mechanisms put on a circular base. And then these crankshaft mechanisms act on rigid links, 6 rigid links that go to whatever vehicle you want to put on it. In particular, you see here a motorcycle. Yes, of course, this new mechanism, which is under construction now as a first prototype, independently from a motorcycle, but in this case, very suitable for motorcycle, let's say, can be mounted on any type of our low frequency stage that we use for handling. A configuration example could be this. In reality, again, we did not think exactly what could it be, the ideal configuration for a motorcycle, but the system is quite flexible in terms of design, also because there is a sort of independence from, for example, electric motors and the entire mechanics. So you can think about this electric motor to be put in any angular position relative to each other. And then you can think about this bar can be as long as you want, the crankshaft mechanism can be adapted. So it's really a new family of motion platform that we are introducing. And in this case, it's entirely VIA grade behind the development of the platform from mechanical point of view, electronic point of view, control system point of view. One interesting aspect of this platform, if you consider an hexapod, for example, that has the same footprint, because when talking about simulator, of course, you cannot compare a 2-meter simulator with a 15-meter simulator. So let's talk about a couple of meter footprint simulator. Then this hexarod can guarantee a motion envelope, as you see in this picture, which when you introduce contemporary, more degree of freedom, the motion envelope of an hexapod is tiny. It's a super small thing compared to what we can obtain with hexarod. Now, motorcycle dynamic is clearly one of the most intuitive situation in which you need contemporary motion, right? If you want also an aircraft, but for example, an aircraft does not yaw. So, okay, an hexapod can do quite a good job for an aircraft because a lot of pitch, a lot of roll, a little bit, but no yaw. In reality, you also yaw with the motorcycle, so you have to take into account all this. So I have a slide that tries to illustrate the control logic of this, including the control of the rider. This is a very schematic thing. I took advantage of an existing 8-cable robot work that is known around. A few years ago, the Max Planck Institute in Tübingen used an 8-cable robot, a gigantic 8-cable robot. I don't know if you have seen it in some movie. They wanted to do a sort of helicopter simulator, I don't know what. But the principle is that with 8 cables, you can control 6 degrees of freedom in a rigid body. You need two cables more than the degree of freedom. You control why? Because cables don't transmit compression forces. So you always need cable intention. So 2 cables are always used to maintain the preload, okay? And I thought, okay, what if instead of moving the entire motorcycle, which this cable robot, for example, has a limitation that cannot do yaw. Because if you do yaw, you have all the cable spaghetti crossed. But if I move the cable together with the platform, then I don't need to have a lot of yaw because the platform does the yaw. So let's use this. Out of this, let's say, simulator, numerical simulator, which is based on bike real time, I obtain the bike real time state, via bike real time state and the rider motion. Then I use those information to feed clearly all the information needed to later on move the platform. And at the same time, I can compute basically the needed cable forces to keep my rider in equilibrium. Because one of the problems that several motorcycle simulators have seen, that you do some sort of roll, more roll, and then you fall down. What is that? Normally, when you do a turn with a motorcycle, you don't fall down because you have inertia forces. But to, of course, implement inertia forces is not easy. And yeah, thanks to this cable robot idea that came to my mind, we can apply properly rope forces to a special gear, to motorcycle rider. Motorcycle rider don't mind, besides scooter rider on the beach, let's say, motorcycle rider don't mind to wear something that is protecting them, as well as they don't mind to wear helmet. Actually, they are obliged to wear a helmet most of the time. So if we build the proper gear, basically we can put in the right point hooks to connect the rider body to the cable system. And then when we have that, of course, from the rope length, we know the position of the rider. Knowing the position of the rider, in real time we feed bike real time with the position of the rider. And the evolution of equation change because of what Professor Gobbi explained. It's very much inertia dependent, the whole thing. We close the loop and we enjoy the ride. Talking about that, and recalling the slide before just as a sketch, let's say this slide is describing what I was talking about, with the addition that we can, of course, monitor also the pedal forces, we can monitor the handlebar forces, all number of information that could be used for what the development of the University of Padua is trying to do to complement maybe unmodelable things in terms of pure algorithm of what's going on. Because if you are a motorcycle rider, you know that pushing a pedal, then you obtain a deviation of trajectory if you don't touch the handlebar. Why? Because clearly you are basically body moves on the motorcycle, and then you affect the inertia instantaneously. So that part is very important. Is the analogy that we have is as we use active seat and belt on a vehicle simulator, we use ropes on a motorcycle simulator, basically to feed what is missing from the motion platform. Of course, I could have certain cases like the one I'm showing you now, in which the motion platform by itself can do a complete job. Because like in this case, the weave oscillation requires more space. And I have the rider on top, and he's subjected to weave, his body has all the inertia forces, and so on. Even for this type of maneuver, I can use the motion platform with an extension of X and Y and big yaw, making slide in the entire hexarod. Thanks to the work of Nico, I was able to compare basically one-to-one the important state of motorcycle dynamic for a simulation in the traditional environment or a simulation on the simulator. Basically, for this maneuver, I don't need any rope because the transients are, in the correct timing to obtain inertial forces on the body that are physically realistic for the rider. Of course, then, you see this quite fancy movie. Of course, I have situation in which I want also to include other realistic effect, like for example, if you ride a motorcycle, you have always air. I don't know a situation beside maybe running on the moon in which the air does not affect the dynamics. So we thought, okay, let's use the air. Actually, in the case, this example of fan is not only for having drag forces on the body, but also to cool the motorcycle, because my idea is that we have to put a real motorcycle on the simulator. One can invent whatever, but a motorcycle is something that is so much connected to the body that if you don't really have super sophisticated things that make then very difficult to achieve the goal, is better to use a motorcycle. Or at least it should be possible to use a real motorcycle on the simulator. So the fan, guess what is used for? For cooling the engine, because I want the engine to also be fully working on the simulator. Okay, I show you this movie in which the rider is in the cage controlled by the cable. Sooner or later, we need a cage also for some safety reason. Then I have, the idea is to have the entire motorcycle. We can put shakers on the front wheel and rear wheel. We have enough powerful shakers to make vibration. And then the motorcycle transmits vibration with an engine and with tire forces to the rider. And the best thing is to generate oscillation where they start on a motorcycle. So the engine and the tire or the suspension hub should be excited. And as you will see in the next days, this new functionality, so to complete the feedback, complete the immersion of the rider or the driver with high-frequency vibration, change the game in driving simulator, and we think also in riding simulator. Because for too long, and in many situations, in the development of driving simulator, let's say all these effects have been ignored and say, okay, the MBH guys, yes, they can sit just in a simple cockpit and feel vibration. In reality, your body feels everything. You cannot separate your brain. Now I don't want to feel vibration, I want to feel only dynamics. Now I don't want to hear acoustic, I have to see only visual. In a real vehicle, could be the worst vehicle ever, you have everything. So you have complete spectrum on your brain. Your vestibular system, your haptic system, your perception system, everything. And the reason many cases why you have motion sickness is because the simulator is trying to tell your brain, hey, you work separate, okay? Don't worry about vibration. And then the brain is used to reality, say, okay, I feel vibration. Why don't I have vibration? So start be preoccupied, I don't feel vibration. Then I notice something in the visual that is wrong. This is not real. Okay, if the brain, which is, of course, is you, probably, is distracted by most sources, then this paranoia of noticing what is odd is gone. So the best way to resolve the motion sickness problem is to feed the brain with many information, all the possible information that one can have. And the vibration is one. And the air, if I have a motorcycle with a helmet at a certain speed, the air noise is one of the most important things. Not mentioning 300, because it probably is the only one. But even at a speed above 100, I would say. So, how much time? 33 seconds. Minus. No, plus. So basically now, trying to connect my presentation to the excellent work of Mattia and Enrico, shown before. What can we do now if we implement this principle? Well, basically, there are several things. I try to make an analogy to what we have done with driving simulator. So basically, it is the same principle. We have a human driver using carrier time as a source of physics, numerical physics. Then we have all this type of feedback. Again, the active seat and belt is the example that we use for the driving simulator. And if I put the riding simulator with this coaching principle, the idea is clearly that I have a human rider on the bike. He tries to follow a certain maneuver, but I also have developed a virtual that can suggest basically to the human how to ride or also how to drive. Mattia's group has developed in the past some coaching for the virtual driver, some coaching principle. You want to speak with him for that. So that is one thing we would like to do with the success, keeping in mind the success we had so far with the driving simulator. Again, there will be synergy between the offline and the online, in the sense that it's very difficult to model the rider, but it's also very difficult to develop a control that is not taking into account all. So for feeding the rider with the right model, you need the real rider. So the loop becomes very virtuous if you connect the one to the other. And that is, I would say, one of the advantages. Actually, I am surprised, while until now, big companies, big motorcycle companies, even Italian, don't say, hey, we need a riding simulator. I am patient.
That's why we are here for, Diego.
Yes. The last slide I want to show, because I don't know for how much, but not much, is, no, zero. I don't see anything, okay. Is using one of the slides of Enrico, he was showing the error that on the trajectory that we are making with the augmented, let's say, motorcycle dynamic or the traditional. Very nice. After working on the Windows movie action, fine. You have seen also visual. So this is the difference for the rider. So if you consider the variation in trajectory, look at the difference for the rider. On the top, you see the delta in the steering angle, maybe 0.2 degrees. And in the other slide, interesting new variable Enrico came up with is throttle minus brake. Throttle minus brake makes sense. And you see that this little difference had the consequence of having very different trajectory. So you can imagine how useful could it be to have a coaching behind the scene, coaching rider on the simulator. Because it's difficult sometimes to explain what to do to a non-rider, even to a rider sometimes. Okay, thank you for your attention.